In order to begin analyzing the motion of objects, specifically those traveling in one dimension, at the next level, I'm going to ask you another simple question, which again has a little bit more of a complicated answer. So imagine, if you will, this old man. Okay, we have this old man. He's going to walk 100 meters, and he's very old, so it takes him a very long time. It actually takes him 240 seconds to kind of walk that 100 meters. So it takes him almost 4 minutes. So it's a very long time. Most people would look at that situation and say he's probably not going very fast. Alternatively, at the same time, while he's walking his 100 meters, I don't know, maybe it's his weekly exercise, a younger athlete decides to run one lap on the same track. So that younger athlete runs 400 meters in 60 seconds. So it takes him 1 minute to run 400 meters, while it takes this old man 240 seconds to only go 1/4 this far. So the simple question I have would be, who was faster? Was it the young boy or was it the older man? Which one of them was faster? Again, in your day-to-day life, it probably seems very obvious. I would imagine most people would say the boy. I don't think anyone would really ever say the old man. And it is correct. I mean, the boy technically is faster. However, the old man is also faster, which doesn't exactly make sense, but this goes hand in hand with what we just looked at with distance and displacement. When we talk in terms of physics, we have to be more specific. Saying something like who was faster is a very general statement. So let's go back really quickly and look at these concepts of distance and displacement. If you remember, in the original video or the original lesson, the question was asked who went farther, and that kind of brought us to a situation where we realized there was more than one answer. And that came down to the fact that it depended whether we were asking for the distance, which is the total ground covered by a moving object, like how much ground is actually passing underneath it, versus the displacement. How far is that object now from where it began? So hopefully you remember that distinction, and that distinction allowed us to better answer who went farther. So now we need a new distinction to be able to better answer who went faster. And that's going to come down to the concepts of what are known as speed and velocity. Speed, you're probably very used to, speed limits, things like that. Velocity, you've probably heard of, but you may not fully understand exactly what the term velocity actually encompasses and how velocity is different than speed. So going off of these two concepts, it's the next natural step to say, well, when you say who is faster, are you talking about the rate at which the object is covering ground, like the rate at which the ground is kind of passing under that object as it's traveling? Or are you talking about the rate at which an object is changing its location, the rate at which it's moving from where it started to where it's going to end? So you can see they're similar, but they are two technically different questions. And therein lies our new definitions. If you're talking about the rate at which an object kind of covers ground, so to say, you're talking about speed. And the more technical definition is the rate at which an object covers distance. So if we're not concerned with the beginning and the ending point, we're just concerned with how fast the object is moving, so to say, while it's going between those points, we look at speed. It's the rate at which the object covers distance. So as time goes by, what distance is this object covering? On the other hand, if we're talking about velocity, if we're not concerned with the rate at which an object covers distance, the rate at which that ground passes underneath it, we're more concerned with the rate at which this object is being displaced, basically from its starting position. So what's the rate at which this object is moving from its starting to its ending point? An analogy I use sometimes would kind of be like if you were to get in your car and drive from, let's say, New Jersey to California. There's obviously no straight pathway. You can't just barrel through buildings, so you have to take highways. And let's say you decide to take all sorts of side trips along the way. So you start in New Jersey over here, and you go all the way down to Florida, and then you go all the way up. Go into Canada for a little bit, and you take your time going up and down and up and down and up and down, and then you wind up in California. Well, let's say you actually were driving 600 miles an hour while you were doing that. Well, the question is, were you traveling very fast? Well, that depends. You were certainly traveling fast if you're just considering like the rate at which you were covering distance. You're moving very fast. You're flying an incredible distance in a very, very short amount of time. However, because you're going up and down and up and down and up and down, if you're just looking at how quickly you're getting from New Jersey to California, it's actually not that fast. You're spending a lot of time going up and down, so your right to left motion is actually not 600 miles an hour. So while you're flying down here and flying up here and flying down at a very high speed, the velocity or the rate at which you're actually getting from New Jersey to California, that straight line distance, is actually not moving at 600 miles an hour. So they're kind of a little example I like to use to show the distinction between the two. In order to calculate them, based on these definitions, since speed is the rate at which an object covers distance, it should hopefully be straightforward that the speed of an object is just equal to the distance it's traveled divided by the time it took to travel. Distance is measured in meters, time is measured in seconds, so hopefully you see that the unit here would just be meters per second. Velocity, since it's the rate at which an object is being displaced, we're still concerned with the same amount of time, but now we're concerned with the displacement. What's the distance from where it started to where it ended? We don't care about all the extra distance it covered in between. How quickly is it getting displaced from its starting to its ending point? So you can see the mathematical distinction comes from the fact that one is based on distance, the other is based on displacement. The unit is still meters per second, but you have to realize displacement is meters plus a direction, and time is measured in seconds. So you really get meters plus a direction divided by time, or we simplify that and say velocity has the unit of meters per second plus some direction, whether it's north, east, south, west, left, right, up, down. It's going to depend on the situation. But it's the same unit, you just have to add direction, much like distance and displacement have the same unit, but displacement requires that direction. Just to simplify it, in case you see, speed is usually represented with a lowercase s, distance a lowercase d, and time a lowercase t. So you will more typically see this as your equation for speed. It's the same thing, just using variables. Velocity is also the same. V, lowercase v, is usually velocity. Time is still t. We do usually say delta x, or also known as the change in x, for displacement, because we're typically kind of looking at like the x-axis. So if an object is moving to the right or to the east, so to say, it's usually along the x-axis. We're not usually going to be looking at things that are moving up and down. In that case, we could certainly say that's like the change in y, but we usually just say change in x because we're generally looking at examples where objects are moving side to side. So just get familiar with these variables and these units because that's going to become important moving forward. So if we go back and revisit that question, who was faster, this old man or this younger boy? Well, now we have some equations, so let's find out. If we look at the old man, his speed is calculated dividing distance traveled by the time it took. Well, he traveled 100 meters. That's how far he went. That's the amount of ground that passed under him, so to say. It took him 240 seconds, so his speed was 0.42 meters per second. That's less than half a meter per second. That is very slow by kind of everyday standards. If we look at his velocity, well, his displacement was 100 meters east because he was traveling in the rightward direction, so we'll call that east. So he traveled 100 meters east in 240 seconds. So while it is very similar, it's 0.42, but it's meters per second east. So there is a distinction here. This is technically 0.42 meters per second in any direction. This is 0.42 meters per second to the east. So you can see in either case, it seems like he's traveling very slow. So your original assumption is probably correct. If we look at the boy, well, his speed, he traveled a distance of 400 meters in 60 seconds. That calculates to 6.67 meters per second. So that means every second that passed by, he had pretty much traveled almost 7 full meter sticks or 7 full meters from where he previously was. So you can see right off the bat, he is traveling significantly faster than this old man in terms of speed. The reason why I emphasize that point, if we calculate the boy's velocity, he had no displacement. He ran 1 full lap, wound up where he began, so he had no displacement. If I divide 0 by any amount of time, I get 0. So if we talk about speed, the boy was significantly faster. He was covering ground at a much higher rate. The old man, however, technically had a faster velocity because he was moving from his starting point to his ending point. Granted, what we would normally call at a slow rate is still higher than how fast the boy was traveling from his starting to ending point because he wound up exactly where he began. So this boy's velocity was technically 0 because he didn't go anywhere. The old man's, despite it being a low value, is technically higher than the boy's because he did have some rate at which he was moving away from where he started. A little bit of a complicated topic, but hopefully you're starting to see how these two are similar yet different. All right, so again, listing the speeds and the velocities, you can see the old man, higher velocity, boy, higher speed. Really quickly, it's important to point out that these are what we would call average speeds and average velocities. A lot of you are probably looking at this and saying, how could his velocity be 0 if he was moving? Well, it's the average. So just to show you, I've drawn like a small track, and at 10 seconds, we'll say the boy was here. At 20 seconds, so on and so forth. He'll be at different points. Each of these points has a different time, and you can see these green lines represent his displacement at that specific instant in time. So you can see that I have 5 different displacements. I have 5 different times. So despite the fact that overall, because he didn't actually go anywhere and wound up with an average velocity of 0, at any given instant, he did have some kind of velocity. We're going to get into that in much more detail later, but I did want to clarify why this doesn't seem to make sense. Because technically, he had some velocity that was going to the right here. Up here, he had some kind of velocity that was going to the left. That cancels out. So overall, it winds up being 0. But just realize these are average values for the entire trip. At given instance in time, he certainly did have some kind of velocity. He certainly did have some kind of speed. And at that instant in time, it may or may not have been faster than the man. But right now, we're speaking in terms of the very simple average speed and average velocity for the entire trip. So we're kind of averaging all of these together. And because he was traveling in different directions at different times, some things canceled out and you wound up with a 0. We'll get into that in much more detail later on. All right, so here's an example. You can give it a shot. Here's what happens. In gym class, we have this boy, Carl. He's running the shuttle run. If you've never run the shuttle run, you start at one point, you run down, pick up a block, come back, drop it off, go back at the second, and return it. So you're basically moving these 2 blocks one at a time from B to A by running from A to B to back to A, and then back to B and back to A. So you're running back and forth twice. That's what's essentially happening here. He runs from point A to point B, picks the block up, returns it, drops it off, repeats that motion. It takes him 20 seconds to do this. Based on that information, he's going here and back in 20 seconds. My question would be, what was Carl's average speed and what was Carl's average velocity? So I will leave this diagram here. I recommend you pause the video right now. After you've tried that, you've attempted that problem, replay the video or just hit play and you should be able to see the solution after maybe 5 or 10 seconds, and then you can double check whether or not you grasp these concepts. Well, the solution to this problem, well, if we look at Carl's speed, he went from A to B, and then B to A, and then A to B, and then B back to A. Each of those paths was 10 meters, so his total distance was 40 meters. 40 meters divided by the 20 seconds it took him to do that, his overall speed was 2 meters per second. Hopefully you got that correct. Carl's velocity should be significantly easier. He went from A, that's where he started, and he pretty much ended at A. He had no displacement. So his average velocity for this entire trip was 0. Why? Because he didn't end up anywhere different than where he started. So the rate at which he got from his starting to his ending point is 0 because he didn't go anywhere. His ending point almost doesn't exist because it's his starting point. We'll take a look at more examples like this moving forward, but hopefully these 2 you got correct.